All right, here's the problem. We have a snowboarder getting dropped out of a helicopter and lands on a snowy slope. So first, I'll draw just a picture. This is not a free body diagram. It's just a picture. So here's the snowboarder, and he is snowboarding down the hill, going this way. All right, so let's look at the forces acting on this guy. The first thing we have is gravity pulling him straight down towards the center of the earth. Okay? We then have friction resisting, right? Friction resists the motion of an object. So if it's sliding down to the right, friction is up to the left. And then we have the hill, which is resisting gravity, but it can't resist straight up, so it resists perpendicular to gravity. So there's just our rough picture, just a rough sketch. But now what we need to do is draw a more accurate free body diagram. So here's our snowboarder. And so what we have is gravity acting straight down. This is the force of gravity. We have friction resisting straight to the left. This is the force of, since he's moving, it'll be kinetic friction. And then we have the normal force acting perpendicular to the surface, and we'll call that F sub n. All right, so there's our picture. And so from here, we need to read the problem. The problem says, find his acceleration. What will be his acceleration, if he will accelerate at all? So the first thing we do is find the acceleration. If it's 0, we say no, he won't accelerate. But if it's not, we try to find it. So what's unknown is A, acceleration. What's known is the angle is 42 degrees. The coefficients of kinetic friction is equal to 0.24. His mass is equal to 90 kilograms. And that's it. All right, so how do you solve this problem? How will we find if he will accelerate? Well, the question is, what law are we going to use? What equation will we use? And the answer is simple. It'll be Newton's second law. Newton's second law says the acceleration of an object will simply equal the net force acting on that object divided by its mass. So all we need to do is find the net force acting on the object, but clearly the net force in the y direction won't necessarily matter. We want to know only the x direction, because in the x direction is the direction of his acceleration. It's pretty clearly seen that this object is going to accelerate only in the x direction because we're defining it now as downhill. There's the x direction, there's the y direction. We've tilted our axis, so now that the x-axis is parallel with the hill. So that makes our angle here theta. So if we can find the net force in the x direction, we simply divide it by mass. So let's go ahead and try to do that. Let's try to find the net force acting in the x direction. All right, the first step in doing that is by doing a sum of forces equation in the x direction. So what we do is we simply say the net force in the x direction is going to equal m times the acceleration in the x direction. And there it is. That's what we're looking for. All we need to do is find that unknown a. That's our answer. All right, so let's bring this down and try to solve for that unknown a. We know the mass. All we got to do is find the net force. There we go. We're in business. All right. So let's open up the net force in the x direction. Let's take a look at it. We have the force of kinetic friction acting in the x direction. And it's acting at 180 degrees, or -1. So force of kinetic friction plus the force of gravity is also acting in the x direction. But not all of it. Only cosine of its angle measured from the x-axis, which is this angle here. Only that angle. Okay, and that angle is going to be the cosine of 270 plus theta. All right, and all of that is going to simply equal, m times a sub x. So it seems like we could solve for ax, but we don't know the force of kinetic friction. We don't know the force of gravity. We need to unpack them a little bit more. So let's unpack it. First of all, the force of kinetic friction times the cosine of 180 simply becomes negative force of kinetic friction plus the force of gravity times the cosine of 270 plus theta equals m times a sub x. All right, so there we go. Still, we can't solve for it. We don't know the force of kinetic friction, so we open it up. And we say the force of kinetic friction, nope, we can open it up right now. We say the force of kinetic friction is equal to the coefficient times the normal force, which is an equation that is always true, plus the force of gravity is equal to m times g times the cosine of 270 plus theta equals m times a sub x. Again, it looks like we can solve for it, but we don't know the normal force, right? We don't know this quantity. We don't know the normal force. We know the coefficient, we know the mass, we know the gravity, we know the angle, we don't know the normal force. So what we need to do is we need to solve for the normal force. And the way you do that is by finding a sum of forces in the x direction, in the y direction. If you notice what we just did the sum of forces in the x direction. We need to now do the same thing in the y direction, because if you look at it, the normal force is simply going to be equal to the force of gravity in the y direction. So let's go ahead and do that. All right, so we say the net force in the y direction is going to equal m times a in the y direction, which we know is going to equal 0. So let's look at the sum of all the forces. We have Fn times the sine of 90, which is 1, plus Fg times the sine of 270 plus theta, and that's going to equal 0 because the acceleration vertically is 0, because when you slide downhill, you don't go up in the air into the mountain, unless you're me and you fall. Okay, so there we see the normal force that we're looking for right there. So if we can open it up a little bit further, we say the normal force times the sine of 90 is 1 is going to equal negative Fg times the sine of 270 plus theta. Well, the force of gravity simply equals negative m times g times the sine of 270 plus theta. So there we have it, right? That is that normal force that we were looking for, right? That's the amount of force that the hill or the slope is pushing on the guy, and that is going to affect the friction. So what we do is pretty awesome. We take the normal force that we solved for and plug it back in here. So let's go ahead and do that. And since I have a smart board, I can just do this. Move it down and create some space. So when we take the normal force and plug it in here, what we get is the negative coefficient of kinetic friction times the normal force, which we just solved for, is negative, and I'm going to put the m and the g together, times the cosine, sorry, the sine of 270 plus theta. I took away those parentheses because there's a lot of parentheses here. Okay, so there's the normal force plus. Now we need to add the force of gravity. Plus, again, I'm going to take the cosine, or the parentheses, away. mg times the cosine of 270 plus theta. And that's all going to equal m times our unknown a sub x. The cool thing about it now is everything, if you notice, is known. We know the coefficient, the mass, the acceleration of gravity, the angle, and we're looking for acceleration. So here, guys, is simply solve for your one unknown. And in doing so, you see that there's a mass in every term. Here, here, and here. So that means they can cancel out. So the mass does not play a part. So what we can do is simplify this to equal negative coefficient times negative g sine of 270 plus theta plus g times the cosine of 270 plus theta. And that is going to equal our acceleration. From here we can plug in our knowns. So we have negative 0.24 times negative 9.81 meters per second squared times the sine of 270 plus 42 degrees plus 9.81 meters per second squared times the cosine of 270 plus 42 degrees. That's all going to equal our acceleration in the x direction. So we can calculate this out. And when we do that, we have negative 0.24, negative 0.24 times negative 9.81 times the sine of 270 plus 42. All of that is plus 9.81 times the cosine of 270 plus 42. And you should get an acceleration in the x direction equal to 4.8145 meters per second squared. We need to round it to, I believe, two significant figures. So we have 4.8 meters per second squared, and we do not need a direction because we're only talking about the acceleration in the x direction, which is clearly either positive or negative, to the right or to the left. So the answer is yes, it will accelerate at 4.8 meters per second squared.